This is Mrs. James continuing our end of course exam review, and this is Astronomy Part II. Last thing we talked about was the concept of redshift. Redshift is associated with the Doppler effect. It indicates to us that the stars and galaxies that we see in the night sky are moving away from us and making those wavelengths stretch out so that their electromagnetic spectrums are being shifted towards the red end of the spectrum. And the last thing we discussed was Hubble's law and how from redshift we can determine that the farther away a galaxy is from us, the faster it's moving compared to us. And that's helped us figure out how fast the universe is expanding. And remember, it's not that everything is expanding away from Earth. Earth is not the center of the universe. Earth is one of the many things, everything in fact, that's expanding, and we're all moving away from where everything started, and that's the center of the universe. Alright, so this concept of redshift was one of the major pieces of information that was used to help develop the Big Bang model. Right. Big Bang model is a widely accepted theory. As a reminder, the word theory means explanation, so the Big Bang model is an attempt to explain a lot of the things that we see and a lot of the information that we gather from the night sky. So here is the details, again, of the Big Bang model. 12 to 14 billion years ago, the portion of the universe that we can see today was only a few millimeters across. So, huge, huge thing now, teeny, teeny, tiny thing way back then. It expanded explosively, and then it continued to expand quickly, and it still continues to expand today. Now, eventually it started to cool down. It cooled down enough for atoms to form. So we had matter, but it wasn't atoms, so it was matter in a sense different from how we understand matter today. Gravity pulled those atoms together into gas clouds that eventually became stars. Right? So let's focus now on what a star is. A star is a sphere of gas. A star is going through this epic battle. There are forces that are trying to make it collapse, and there are forces that are trying to make it expand. Gravity is what's trying to get it to collapse. Okay, all those different atoms are attracted to each other. They're pulling in, creating greater and greater pressure. But there's a nuclear reaction going on inside, and that's trying to make it expand. The gravity is, interestingly enough, also the thing that's causing the pressure that causes the atoms to go through the nuclear reaction of fusion. So gravity is responsible, deep down at the root of it, for both of the things that are going on, taking part in the battle. So let's talk a little bit more about that nuclear reaction. There's hydrogen atoms inside the star, and they are fusing into helium. And as they fuse, they release energy. There are other nuclear reactions going on inside stars, and those nuclear reactions lead to the creation of all the other elements. So anything that's inside you was originally inside a star. So if someone says that you're made of the stuff that stars are made of, well, yeah, it is actually true. Alright, eventually the star collapses as the hydrogen runs out and gravity wins. So I just said that there's an epic battle. Gravity's trying to collapse it, but nuclear reactions are making it expand. As it runs out of fuel for this nuclear reaction, gravity wins, and the star starts to collapse. But this brings together the atoms of other kinds of elements closer together to each other inside the star. When they get closer together, they start to go through nuclear reactions too. And this makes the star expand again. Now for some stars, it makes it expand drastically. Our sun is not going to expand drastically, it's going to expand normally, but still it's very likely that Earth itself is going to be inside the sun. That's how much bigger we're thinking that our sun's going to get. And that's so far in the future, there's no sense even worrying about it. It's not like this is going to happen next day or in 1,000 years or even in 10,000 years. This is way in the future. Now, eventually that fuel is going to run out too. And that might happen pretty quickly. So for some stars, that can be a quick use of that second round of fuel. And then those nuclear reactions stop too. And all the gases that are around the star began to dissipate. That means they just kind of float away. leaving behind a small remnant. A remnant means just a little piece of something, so there's just hot, hard stuff that's left behind where the star used to be. This whole thing here is what I'm going to refer to as the life cycle of a star. So a star's not alive, but we can still talk about its life cycle. Alright, this process is a little bit different for stars that are of different sizes. So the same basic pattern, nuclear reaction, runs out of hydrogen, shrinks, expands, and then slowly stuff floats away and you're left with a remnant. It's going to be a little bit different though. Medium and smaller stars, and our star is a medium-sized star, they tend to behave the same way. That remnant that's left up at the end is called a white dwarf. Big stars tend to have a larger explosion when they run out of their hydrogen and they collapse and then they expand, and that is often called a supernova, and the leftover part at the end is called a neutron star. So it's a little more exciting, and we have actually seen those explosions. We've actually recorded those on film. There are also some historic records. For instance, in China, several hundred years ago, people observed a supernova that was so big that you could see it for 2 or 3 days during daylight. We could still see it looking up in the sky on Earth. Alright, really, really big stars tend to end up as black holes. So, even though we have the same basic pattern, the 3 different broad categories of stars go through that pattern slightly differently. Well, what makes us think that this is true? We don't live long enough to watch an entire star's life, not even close. So why do we think that this is what happens to stars? Well, some of the changes we can see. For instance, like I said, we have seen some supernova. And there are many, many stars out there in the sky and many, many different stages of life. So we can piece together the different information, and that's what gives us our model of what we think a single star's lifestyle is like. Might we be a little bit wrong? Yeah, but that's kind of how science is. As we get more information, we change our ideas. Alright, here's a nice picture of it. We have our small, medium-sized stars like our sun. Here's the expanded state, and there it is at the end, it's the white dwarf. Here's a larger star, it goes through the process, turns into a neutron star. Here's a big, big old star, goes through the process, turns into a black hole. Okay. Now let's look at that same picture but a little bit more detail. And this is probably a lot prettier than what you have in your handouts. I'm going to add an extra step. The first step is called a protostar. So before it becomes a star, it's a protostar. Then it turns into a regular star. Right? Here is a sun-like star way down here. Alright, there it is. So there are some small stars that are smaller than our sun. Some of them are called red dwarfs. The teeny tiny stars are called a brown dwarf. This brown dwarf is still larger than Jupiter. Jupiter is not quite big enough to be a brown dwarf. It doesn't quite have enough gravity to pull the atoms close enough together for it to go through a nuclear reaction. If Jupiter had been a little bit bigger, it would have been a brown dwarf star. So now let's look at bigger stars. We have a blue giant, a blue supergiant, and even bigger blue supergiants. The next picture shows us that expansion stage. So our star is going to turn into a red giant, and then all that dust and gas is eventually going to float away, leaving the white dwarf behind. So here we see a bigger star, okay, becoming a red giant. And here's the supernova, that's that huge explosion, and all that's left is that little tiny neutron star. And here you can see that these bigger stars go through a similar process, even more fantastic explosion, and then we end up with a black hole at the end. Right? Now all this dust and gas that just kind of drifted away from the stars, this now becomes the matter that new stars form out of. So the process begins all over again with new stars. Alright, good place to stop. We'll pick up next by talking about the classification of stars.